I'm happy to make a short presentation about a specific project that our company has been working on with the city of Ottawa and other companies that are based actually in the Ottawa area. But first, I'll just review a bit about myself. So I have a bachelor's and master's degree from the University of Calgary, which is just south of Edmonton, Damien. You probably know. And while I was doing my master's degree, it was concentration on investigating autonomous control of steam turbine generators, which used to be the primary source of electric power in Alberta at a place called Lake Wabamun, just southwest of Edmonton. And when I finished my degree, I came out east to Ottawa. In those days, basically the only place to work after getting a degree in science electrical engineering was Bell Northern Research. If you wanted to advance your career, because it was kind of like going to a postgraduate school. So worked there for several years, and then I went to work for a company that's today called Kongsberg Geospatial. And then I left Kongsberg and I worked for a company that's today is called Curtiss-Wright Controls. They all have, I'm using their modern names because many cases, which is common in Canada, startups get acquired by other companies. So Kongsberg acquired a company, Curtiss-Wright acquired a company. Arc Cores is actually the result of a four-way combination of a company I started, plus two companies in the US, one in the UK. And we formed the world's first chipless, fabless semiconductor vendor. And then I left there shortly after we did our IPO, and I became an advisor to a company called Noble Vision Robotics, which was developing a robot in those days to keep birds away from grapes. And this was before there were drones, so it was a more complicated technique. And then I left there to join Frontline Robotics and eventually founded 4D Robotics. So the types of applications I've worked on are in the area physical security, hazardous materials, healthcare, airport luggage handling, analog lunar Mars exploration, and agriculture. So this is just recently my career. You can imagine that, our clients have included NASA, the Canadian Space Agency, the Royal Canadian Mounted Police, the FAA, as examples. And currently, our main focus of our company is to investigate applications of multi-domain autonomous vehicles for safety and security. So a domain, ground is a domain, air is a domain, on water is a domain, underwater is a domain. We actually have an experiment in the Halifax Harbor involving air, on water, and underwater. And that's just one early application of this technology. But the real motivation for the project I want to talk about is a result of research being done in Canada at the government level with the long range goal of having what's called high frequency rail. So that's a rail track probably equivalent to what already exists in countries like Italy and in France that provides a much more rapid transport along the main corridor of Canada, of the industrial area of Canada, which really starts in Windsor, Ontario, and goes to Quebec City. And so there's some stats that I've put up here. And this is specifically a Canadian context. We're a very broad country, so our railways tend to go east-west. And of 23,000 ground level crossings over 26,000 miles, there have been in the 10-year period up to 2022, 11,000 accidents. So ground crossing is where the vehicle or the pedestrian and the crossing are at the same level. So you actually have a gate that comes down. And of those accidents, there have been 233 fatalities and 288 serious injuries. And it turns out that this is statistically, these types of crossings are not the most serious in terms of the accidents that take place, which are derailments, but they're the second highest. And so the Transport Canada wanted to investigate that, and I'll somehow figure out how to send Philippe the presentation, but there's a link there that goes over those statistics. So the motivation is to find out ways of making railway crossings at the ground level safer. So I'm showing you a picture here of an area where we can do testing, and for some reason the A doesn't show up. It's area X.O, private autonomous vehicle test track. This is actually a Google picture of most of West End, Ottawa. I'll move my mouse over to the center. This is the center of the test track. From there to downtown Ottawa, in a straight line, is about 15 kilometers. So it's right downtown. Our office is actually up in the left-hand corner here, and this is where I'm speaking from. This is my house. So from here to there is about 4 kilometers. So it's right almost in the middle of the city, and it's a repurposed agricultural farm. And on the next slide, essentially zoomed into the top of it, you'll see the test area for our testing. There's a real railway track here, but obviously there's no vehicles coming in. And there's a conventional crossing controls, Siemens has developed this for this crossing. And there's a control box here and a mast where it was installed where we put a lot of sensors. So this is where all of our testing is taking place for this example. And this is an overview of the entire project. It involved roughly 15 companies, all local to Ottawa, plus suppliers of commercial off-the-shelf equipment, such as Capsch, Siemens, FLIR, for example. And I'm only going to talk about the part where we work directly, which is this slide. So the idea was, how do we make the crossing safe for potentially a snowplow coming up to a railway crossing? And in Ottawa, we actually have 42 grade level crossings. It's a big area of interest for the city. One of the problems that they've had is when the snowplow goes across the railway track itself, it's at the ground level, it scrapes and it damages the snowplow, which causes quite a bit of damage. We have 326 snowplows for Ottawa, and the service level agreement is during a storm, the snow must be removed by the next day so that people can go to work. So the problem is that the snowplow operators, basically go in 13-hour shifts, 13-hour shifts in any type of weather condition. And so they actually can't drive the snowplow safely when it's dark and it's snowing, it's sleeting. They think they can, but accidents happen. And 2 years ago, one of the snowplows actually got stuck right on the railway track. So it had to stop all the rail service, try and get this vehicle removed. So we got involved in this project to take some of the technology from the snowplow and apply it to this. And it's very difficult to get the city of Ottawa to lend us a snowplow so that we can test frequently. And what we did was we convinced Transport Canada that we could take our own test vehicle, which is autonomous, and have it emulate the properties of a snowplow. So instead of lifting the blade autonomously and driving through, we actually just have the vehicle beep when it detects a railway crossing or when it's been commanded to cross a railway track. And we are integrating with a variety of information coming from a mast on the side. So this is essentially an infrastructure to vehicle application. It's one of few that's testing vehicle infrastructure when the vehicle is autonomous. And I'll just go to the next stage. So that's the vehicle. That's actually the software developer, Brian, who's working on it. Here you see a small antenna. This is the antenna for the infrastructure to vehicle communications. So this is this structure here is where, sorry, go back, is where the regular equipment would be there to control the arm going up and down. And so there's, the status quo is there's sensors somewhere in the track. They detect that a train is coming, they lower the arms, ring the bell. By applying a lot of technology, we can actually detect vehicles coming to the railway track. And basically, the objective is to transmit information to the vehicles to say, this is what's happening around this railway track. You might want to call it surveillance data, or you might want to call it remote data, but it's all done right at the track. And this situational awareness is communicated to the vehicle. And it could be any vehicle, so long as these vehicles are equipped with the right equipment. And it could be indicating there is a pedestrian crossing the track. It could be indicating there are other vehicles coming. It could be indicating there's a train coming. So you want the vehicle to react actually before the railway crossing is coming down, because in bad weather conditions, you'll need more time to stop. In really bad weather conditions, you may not even see the railroad track. This is a common occurrence in Western Canada, and it does actually happen in Ottawa under extreme weather circumstances. So what's essentially happened is an electrically operated gate has been turned into a robot. The robot doesn't actually move, of course. It's like a robot in a vehicle automation line, but there's a lot of sensors that have been added to this crossing, and so that's why we consider it being a robot now. And the robot's just saying, hey, be careful, something's happening. And there are standards that we relied on to take care of this technology, but this is how we install it in the vehicle. This is a CAPS onboard unit, and there's an antenna here. And at the mast, I'll show you the mast in a minute, there's a CAPS roadside unit. And CAPS is a European company. This is commercial off-the-shelf equipment. It's designed specifically for this infrastructure to vehicle application. So this is actually a video of a variety of tests. But before I start it, one of the first shots you'll see is of the mast. So there's the structure that's controlling the railroad track. Here's where all the sensors are located. And it's a very tiny transmitter up here, which transmits to this antenna. And the messages are standard. Unfortunately, believe it or not, we're using ASN.1. And the messages come, they're parsed by the vehicle, and the vehicle will get only 4 out of about 30 messages that are possible. And one of them is that there's a crossing guard coming. There's a crossing bar coming down, and there's a crossing bar going up. When we did the semi-autonomous snowplow, the snowplow actually detected the railway track and reacted, but it didn't know about the crossing guards. So now, instead of us detecting the railroad track, we have the railroad track actually just transmit to the vehicle, which would actually be a safer process. To start this, I'll speak through it because it's about a 3-minute presentation. And coming up will be 2 pictures of the masts. So this is the CAPS unit, the OBU, which goes in there. The roadside unit you can't actually see. It's in this structure. It's just a bunch of wires going up. On the mast, you'll see a variety of sensors. So in close up, there's cameras of various types: spherical camera, direct camera. There are lidars, there are radars. There's thermal cameras as well. We wanted to basically test with as many sensors as possible. So this test is just the vehicle going across the railroad track with the bar going up. I don't know if you could hear the beeping. I don't know if that gets transmitted over the internet. We just repeated it. And so in the next test, you'll see the vehicle coming up to the railroad track, and the bar has been manually dropped. But the system automatically transmits to the vehicle. So see the vehicle come to a stop. It looks like we're out in the country, but we really are in downtown Ottawa. It stops. and it won't move until the roadside unit communicates back to the vehicle. So the fact that the bar is going up and down, the vehicle doesn't care. You see it go through. So basically, we just proved that the messages that we selected are being validated and tested by the vehicle in a variety of experiments. It'll come through and it'll stop shortly after. Okay, then now the next two frames that are coming up show information that's being detected by the sensors on the mast. So in the upper left, you'll see optical information, and it's actually augmented by showing where the zones are for the vehicle to move after it's exited the railway track. On the right side, you'll see a thermal camera. So there is object detection and classification taking place in both. Standard YOLO was used on the one on the left. The one on the right, though, that's a custom package. And I should stop it because you can tell it's custom. Because the object classification isn't working perfectly. It thinks right now that the vehicle is actually a pedestrian. And as the vehicle gets closer, the algorithm finally corrects itself and realizes that the vehicle is a real vehicle. You see there. Now that's because all of this classification detection going on is essentially a reinvention of YOLO done specifically to handle thermal cameras, which don't have the same properties as RGB cameras, and so the training has to be from scratch, and you have to basically just relearn how to do it. So that's why you see something non-traditional being drawn around the object. You'll actually see when the crossing bar comes down, the detection continues, but you'll see sort of trailing edge information. Actually, you don't in this version. You see trailing edge information as it resets to itself. So that's the last slide. So this work was roughly 13 companies in Ottawa, plus we needed to get the cooperation of Invest Ottawa, which operates the Area X.O facility. It's a separate facility, actually funded by the province of Ontario, but operated by Invest Ottawa. And the funds for the project came from Transport Canada. And last but not least, there's subcontract information for myself.